So this video is on equilibrium, a very special state of motion in which the sum of all forces acting on an object is zero. We can write that mathematically. Let's take a moment to do that. This is saying that the sum, I'm going to use a Greek letter sigma, the sum of all forces, sigma means summation, sum of all forces is equal to zero. This is actually a mathematical statement of Newton's first law, that if the sum of the forces is equal to zero, then the acceleration is equal to zero. Okay, so we've said that as an object at rest stays at rest, an object in motion stays in straight line motion unless acted on by an unbalanced force. So if there are no unbalanced forces, the object just continues doing what it was doing. So the object just maintains its present state of motion. Another way to say that is that it doesn't accelerate, so it maintains its present state of motion. Now we're going to demonstrate equilibrium using a force table. A force table, sort of looks like this picture here, has a ring on which there are various strings attached, and we can take on those strings, we can hang some masses from those strings and allow Earth to sort of pull on those masses, exerting a force on that ring. Now I'm going to show you how to create equilibrium using a couple of forces, like we'll take a couple of forces by hanging some masses from that ring and allowing Earth to pull on those at various angles. Our job is to try to create equilibrium by sort of countering those forces that are acting by creating equilibrant force that sort of acts in a direction opposite of the net force of those two things, so that we can create equilibrium. So this is it's a fairly mathematical or graphical way of doing this, but I'll show you with this video how to accomplish that. Before we get into all of the math and all the graphical drawings, let's talk about some applications in which equilibrium might be an important thing to achieve. If I'm building a bridge, maybe I'm a civil engineer and I want to build a bridge to span across a riverway or a waterway. That bridge needs to be able to withstand various loads. Wind and so forth would be certainly some loads that would be acting on it, some forces, but a lot of times there's just a bunch of cars driving across this, and as that car drives across that bridge, the bridge needs to be able to maintain equilibrium so that the bridge does not collapse or start to fall apart. So equilibrium would be a special need for a bridge. Another example might be a sign that we might hang from the side of a building. We want to make sure that the building is able to support that sign, not just the weight of the sign, but in the event that wind blows on that sign, or someone walks by and hits that sign with their hand or something along those lines, that the building can withstand those forces and keep the sign from falling down. Another really good example would be if I'm building a house. Or some sort of building. There are a tremendous number of different forces that are acting on a house at various times. We have some wind loads, so wind hitting this thing from the side. We have some negative wind loads where the wind blows over top of the roof. Bernoulli's principle says that there's going to be less pressure exerted by that fast-moving stream of air, and that would have a tendency to sort of pull the roof off the edge of the building. A lot of times that happens in tornadoes, is that the roof gets blown off of the building. We have this thing called a dead load, which is where the snow sort of piles up on top of the roof, creating a force downward due to gravity. We have live loads of people walking along in the building, or maybe equipment that's placed in the building, or furniture, you name it. Hydrostatic pressure from water pressure in the ground. Those are all different kinds of loads. The building needs to be able to withstand all of those forces and to be able to maintain equilibrium. Now let's go ahead and take a look at how we can do this process of vector addition using a force table. So how can we create equilibrium for an object on which multiple forces act? The weight of 400 grams at 35 degrees and the weight of 700 grams at 160 degrees. Your video, before you keep going forward here, we need to have you change what was stated on your packet. So your packet had the weight of 300 grams. I want you to change that to 400 grams. and you had the weight of 700 grams at some other angle, like 110 or something. I want you to change that to 160. So make sure you make that change so that your numbers are the same as this video is using. Now we're going to do this as a graphical drawing. There could be a mathematical way of doing this as well. I think I'll put together another video if you want to watch it mathematically using vector components. It's a little bit quicker, more mathematical, but a little bit quicker way of doing that. And so if you'd like to, you can watch that video as well. But anyway, if we're going to do a graphical drawing, I need to have a scale. Let's do 1 centimeter is equivalent to the weight of 100 grams. So that makes it convenient. This would be a 4 centimeter vector, and this would be a 7 centimeter vector. And so let's start with drawing a little ring here. That ring sort of represents my origin. Let's put a little scale here as well to say that that's 0 degrees, that's 90 degrees, that would be 180, and that would be 270. Okay, so standard mathematical XY coordinate plane. We need to draw a 4 centimeter vector at an angle of 35 degrees. So let's pull out a protractor. Okay, and let's place that down here where the center of the protractor is at that dot. And let's go ahead and make a mark at 35 degrees. I'm going to make that right there. And let's go ahead and draw a 4 centimeter vector. So this is going to take me a little bit longer than it will you, since I'm doing this with the Smartboard tools. You're just using your standard rulers and protractors on your graph paper. So go ahead and take a moment to do that while I do that here. Okay, so I got my my ruler in place. I'm going to go ahead and draw a 4 centimeter vector, and it's going to be pointed right there. Add a little arrow to it to indicate direction, and let's just, for grins, label that with the weight of 400 grams at 35 degrees. Now, we need to also add to this ring a weight of a 700 gram object that has a certain weight at 160 degrees. So we're going to now do that with this green line here. So let's see. I'm gonna show this via the parallelogram method simply because that's the way that we typically draw FBDs. Just watch this for a moment because you're going to want to draw this maybe differently than the way I'm doing this. So just give me a moment. Don't draw anything just yet if you're following along with me. Just sit tight for a minute and watch this here. We're going to go to 160 degrees. I'm going to mark that right here. I need to draw a 7 centimeter vector, and so that's going to be here. And let's see, I need to rotate this thing around here. See if I can do that. Yep. Pause that for 1 second. Okay, so now I have my my ruler here. I'm going to draw that vector here, and hopefully you're not doing that with me just yet because it's really hard to add these things via the parallelogram method. So that would be the vector that represents the weight of 700 grams at 160 degrees. Now, the reason I draw it like this usually is that on an FBD, we think of those forces as being concurrent, which means they both act at the same time. And really, we're saying that they sort of act through the center of that object. But it's sort of difficult to add these two via the parallelogram method because I'd have to like create a parallelogram up here. It's just as easy when you guys go to do this is try to draw it by, let's take that and I want to draw that portion and I want to switch that and put it up here. So for you guys to do this, I want you to take your protractor and actually place it here and then draw that arrow this way. Okay, so go ahead and take a moment to do that. I'm going to stop this, pause this video, and move that green vector up to there. Okay, so go ahead and try that on your own. Okay, and so hopefully you have something that actually looks like that now. You have a vector drawing that looks like so. Our job here is to try to determine the net force acting on that ring from these two forces. Let me label this also as the weight of 700 grams at 160 degrees. Now, vector addition means that when I do it tail to tip, it sort of spans from the beginning to the end. I'm interested in the net force here because ultimately I'm going to try to counter that net force by what's called an equilibrant force. So I'm going to now go ahead and try to draw the vector sum, which would be an arrow sort of pointed up and to the left. So use your ruler to make that straight line, and then measure the length and measure the angle relative to our x direction. So go ahead and try that. I'm going to reposition my rulers and protractors accordingly. Okay, and so let's see, I'm going to use this, I'm going to use a black line here to draw the resultant force. Would be something that points sort of up and to the left. And I'm going to draw that as a black line. I really should have done it as a dashed line. This is the way that we've been talking about that with you guys. That represents the net force. I could measure that length. And when I measure that length for this graphical drawing, I get about 5.6 centimeters. So that would be this would be the weight of 560 grams at an angle of, well, let's see my protractors here. That angle would be okay. That angle would be, I'm getting that to be in the neighborhood of 125 degrees. So according to 0 being to the right along the positive x-axis, the resultant force would be the weight of 560 degrees at 125 degrees. Okay, so that's this angle there. Now, ultimately, I want to try to create equilibrium. I want to be able to design the system such that the total force would be 0. Right now, I have a total force that would be equivalent to the weight of 560 grams at 125 degrees. So how can I balance that net force and create a force of 0? Well, what I'm going to do is I'm going to take let's see, I'm used red up here for the equilibrant. I'm actually going to now determine what's called the equilibrant force. It's going to be the exact same magnitude, but it's got to point in the opposite direction. Okay, so the red arrow that I've drawn here is what's called the equilibrant. So the resultant of those two, the resultant force would be the weight of 560 grams at 125 degrees. The equilibrant force, the force needed to produce equilibrium, would be the weight of 560 grams, not at 125, but at 125 plus 180 degrees. So it would be at 305 degrees. If I took a 560 gram mass and hung it on that string, or on that ring at 305 degrees, that should end up producing equilibrium, which means that the total force acting on that ring would add to 0. You notice actually what I've created here, it looks like a triangle. And a triangle would with 3 legs would mean that it would start at one spot and end at one spot. Now this particular setup using a force table allows us to visually observe the addition of vectors, or forces rather, that act as vectors. The magnitude and the direction become pretty important on those, as we know. And so your job now, when you set up that, is that when you set up your various weights at various angles, you should see that you would get a net force of 0. So you have this as an activity to do. And so your job is to choose your own set of masses. So I chose 400 and 700. I want you to choose any combination of these things. I would suggest that you maybe do something other than 400 and 700. Do not choose 2 of the same masses. So do, maybe you could do 200 and 500. You could do 300 and 600, 500 and 700. It doesn't matter. But choose 2 different masses. And I want you to choose 2 different angles. Now, every person at your table, each table needs to do the same set of values, because I want you to have one solution. So each table has the same set of masses and angles. Okay. Now, some people may be more interested in doing this not graphically, but by doing it mathematically. If you're interested in doing it mathematically, you can watch this video, another video that I will post for you, just to show you how to do the same thing with components. But many of you should just be able to do this graphically. I want you to set up your force table and have it be observed by either myself or another instructor.